6 to begin with. So that's the first spec point on the assessment. So what I'm going to do is I'm going to run through some mind maps, really. I'm not going to do a great deal on in the way of exam questions, mainly because we've covered a lot of exam questions in lessons now. I have got the odd one, one for like a graph for rates and another one for equilibrium. But other than that, we're mainly just going to look at making some mind maps and just going through some of the key information. So starting off, so spec 6. Put spec 6 up here. Well, this pen's a bit, it's on its last legs. I'll just get let's try this blue one. There we go. That's also not great. I'm stealing your pen, Mr. McDade. So spec 6. So firstly, we need to understand the 5 different ways that we can affect the rate of a reaction. So firstly, we've got temperature. We've also got concentration. Pressure. Surface area. And there's also adding a catalyst. Now, a catalyst I'm going to speak about individually. The other 4 we can talk about in terms of an explain question or describe question. Now, it's almost certain that there might, on your paper, there could be a 3 marker on any one of these, and it will say to you what happens when you increase the temperature or concentration or whatever it might be, one of these 4. What happens when you increase one of these on the rate of a reaction? So there are 2 things that you would put into your answer regardless of whichever one of these 4 you would they have chosen to question you on. So the first thing is you would talk about the frequency of collisions. So for each of these, you're going to talk about frequency of collisions, and if it was an increasing question, increasing. And you'd write the same for concentration, the same for pressure, and the same for surface area. So if any of those are increased, then you're going to increase the frequency of collisions. The different bit is this next part of your answer. So if it's temperature, you need to talk about kinetic. I might just put some keywords, so I might not necessarily write the full answer out here, by the way. So do listen to what I'm saying at the same time. So the kinetic energy of the particles would increase. So therefore, so we're thinking about particles. And therefore, we need to think about the fact that they're going to be moving faster. For concentration, we're going to be talking about there will be more particles per unit volume. And they're the words that the examiners use on the mark scheme. For pressure, you can also say the same thing there, because if you think about it, what's happening in pressure is you basically, and this would be for a gas, so it might be worth mentioning for a gas just in brackets there, but if you increase the pressure on 2 gases reacting, ultimately you're reducing the volume, so there are more particles per unit volume. It's because you're ultimately reducing that space. And then for surface area, it's all about the surfaces that something can react on. So if you've got 2 reactants, one of them, say, is a strip of magnesium and you're putting that into acid. If you cut that piece of magnesium up or you use magnesium powder, then straight away you've increased the surface area, so there are more surfaces. For the reaction to take place at. Now, after this, so you've written your frequency of collisions increases for each of these 4. I'm just going to put a little box around, or just to block this off from catalysts. So you might have talked about your frequency of collisions increasing. You've got your different reasonings. That is the bit that separates each of these answers from one another, depending on what you write. And then the final bit is that all of them lead to the rate increasing. So the rate of reaction increases. So I would just have that as my kind of concluding statement. So rate of reaction increases. So understanding each of those four and just understanding what's happening. It links to the required practicals as well. So you've got ones that are involving changing the concentration. Well, both of them involve changing the concentration. So you just write about frequency of collisions, rate of reaction, but as I say, that middle section of your answer should be something unique depending on what they're asking for. Now, adding a catalyst. This is where we draw on a little bit of Spec 5 information or a bit of Spec 5 knowledge. So when you're adding a catalyst, it's all to do with the activation energy. So firstly here we've got an energy profile diagram. I'm just going to draw two side by side. This is still in shot. There we go. So I'm going to do one for, we'll say, an endothermic reaction. So I've got my reactant starting down here, my products starting up here. So I'm going to do the same. Over. Just going to draw two side by side. So I've got this endothermic reaction. Now, just drawing it normally, you've got this hump as you draw up from the reactants to the products. It's going to go higher because this is your activation energy. So as you can see, the activation energy is quite large on that one. For this one, what we're going to do is we're going to reduce the activation energy. So I'm going to draw them next to each other. So this is the original one, but now what's happened is the activation energy is smaller than it is there. And what the catalyst does is it reduces the activation energy. So you might be expected to draw one of these energy level diagrams. You might be expected to fill one or label it. So what they often like you to do is label this area or draw on what a catalyst has done. So you would firstly, you may have to draw the normal line, which would just be your normal activation energy, which would go up to here. However, with a catalyst, this would be reduced. Another point, I know we did this earlier in the theatre, but always make sure that you're starting from the reactants going up to the peak. And what I've seen some students do before in the past, so if they've got, I'm just going to do a little one here, just as an example. Let's say that is your diagram. Students sort of go, oh, that's the activation energy there. Well, I sort of know what you're talking about, but that would be wrong because you've not gone from the bottom where the reactants start up to touching the peak. So it needs to be really precise when you're drawing that. So what it's doing is it's reducing the activation energy. So there are two things really to bear in mind. So I'm just going to put a little line there to block this information off. So what a catalyst does is it reduces activation energy. So we can see that from our diagram. And it also provides an alternate pathway. And that's for the reaction to take place. So therefore, by providing that alternate pathway, it's reducing the activation energy, and therefore the reaction would be faster. It's the only one really where in your answer you can put the reaction would speed up or is faster. They allow that. Whereas if you're talking about one of these four, you need to talk about these things. So collisions, frequency of collisions increasing, the rate of reaction increasing, and therefore you give your reasoning for each one. So that is your 4 or 5, if you class catalysts as well, of your ways of changing the rate of reaction. Now, in the middle of this spec point, before we then look at equilibrium, we've also got some stuff on tangents. Now, again, I know I did this earlier, but I'm just going to briefly just whiz over this with an example. So here I've got a graph. I'll cover it all up actually. In fact, let's find that there and then that there. Lovely stuff. So on your graph, it might say work out the rate of reaction at 30 seconds. So what I'm going to do is first I'm going to locate 30 seconds on my x-axis, so I know it's here. And then what I'm going to do is I'm going to read up until I'm touching both of these lines. So an X there and an X there. You'll get a pencil. I've got felt tips so you can see this, but in your exam use your pencil because it'll be nice and detailed and nice and accurate in terms of where you've got that. What you're then going to do is you're then going to draw a line to form your tangent. Now I'm going to do it on the top one. So I'm going to do it on the top one. Now when you're doing this, I would try and make sure that one of your numbers is a nice, one of your axes is on a nice round number. So I'm going to go up to 70 and down to 60. So that makes my life really easy because I know that we've got 10 there, and that's going to be centimetres cubed. How do I know that? Because it starts at 60 and it goes up to 70. Reading off on your x-axis, so coming down here, so we're looking at that one there, and we're looking at this bit here. So looks like I've got 12 and I'm going up to 52.5. So I've got a difference there of what, 40.5 I think, on the bottom. Now when you've drawn your tan, if it's easier for you, draw a triangle underneath. That's not an issue. I'm not going to do that just to, you know, with time, we press for time. But you can draw a triangle underneath and it'll make it easier for you to work out what this is on the y-axis, what this is on the x-axis. What you're then going to do is y divided by x. So therefore, I'm going to do 10 divided by 40.5. Not got a calculator on me. That would get you an answer. And then because we've done y divided by x, that's the same thing for your units. So you get a mark for calculating the units correctly. So that'd be centimetres cubed per second. So that is your rates graph. Now moving on to equilibrium. I'm just going to get another sheet so you can't see through that one. Moving on to equilibrium. So with this is to do with, firstly you need to understand what the term equilibrium means. And you also need to understand how you can apply the principles of Le Chatelier on certain reactions. I've got an exam question just to show you because it's easier to show you as a demo. So equilibrium, it's all about the forward reaction and backward reaction occurring at the same rate. So that is the key word there. So forward and backward reaction. Now you know that it's going to be an if it's an equilibrium based question, it's going to give you a symbol like this in the reaction, and that is the symbol for a reversible reaction. So it means that it is reversible because it means it can go forwards, it means it can go backwards. Now there are three ways really that you can affect equilibrium. So you've got concentration, you've got temperature, and there's also pressure. So for concentration, I'm just going to do an example reaction. So you've got A plus B equals C. Now if I increase the concentration of A and B, so they're my reactants, if I have more, so if I have an increased concentration of A and B, then I will produce more of C. If I increase the concentration of C, I end up with more of A and B being produced. So that's quite easy, I would say, concentration, because it's dependent on which one you've got an increase in concentration. What they might do is flip it around. So they might say, what happens if we decrease the concentration of C, which is takes a little bit more thinking. So if they decrease the concentration of C, that's the same as increasing these. So you would actually end up with the reaction going forwards to actually produce more of C. So just bear in mind, if it's increasing, I think it's dead easy, because if they're increasing this, you're going to produce more of this and vice versa. Whereas if they say decreasing, just bear in mind that you're going to have to think, well, if they're decreasing this, that now means we've got more of the reactants, so we'll actually end up producing more of that to fulfill that space, because it's all about a bit of a balancing act and making sure that the reaction reaches equilibrium, I suppose. So for temperature, exo and endo is important. So I know with my classes last year in year 10, we talked about how we talked about lots of equilibrium questions, and people used to look at pressure ones or concentration and go, oh, well, that one's exothermic. This only applies to temperature, doesn't apply to these two, so it's only applying to temperature. Now, if you've got a reaction of A plus B making C again, and this top one we'll say is endothermic, and this one is exothermic, so the backward one is exo. If we had a scenario where the temperature is increased, we need to think which reaction is going to benefit from an increase in temperature. Now, which one needs energy to happen? Which one absorbs energy to happen? So this relies on your Spec 5 knowledge. So that would be the endothermic one. So if we, in this example, if we said we're going to increase the temperature on this reaction, the forward reaction would happen. So we would produce more of C because it's an endothermic reaction. Likewise, if we said we're going to decrease the temperature, the reaction would go backwards because it's exothermic. So that would be the one that would benefit from that scenario. So therefore, we'd produce more of A and B. For pressure, it's all to do with the number of molecules. So that's the important part. I'm going to show you exam question, then move on to spec 7. So number of molecules. So let's say we've got 2A plus B making 2C. So this time we have to count the number of molecules either side of the arrow. So I can see here I've got 2 molecules of A, 1 molecule of B. So I've got 3 that side. This side I've got 2 molecules of C. So it's a 3-to-2 ratio in terms of my molecules. So when you're increasing the pressure, what happens is you're pushing these reactants and these products together. So if you're cramming them together, which ones are going to start to react more? Well, clearly, if you've got more of these are the ones that are going to react. And if they're reacting, what are they producing? They're going to produce C. So this type of question would say, what happens to the yield or amount? And that's a key word that we're looking for equilibrium. I write it at the top. If it says the word yield, we know we're talking equilibrium. If we increase the pressure on this reaction, we would end up producing more of this one. If we were to decrease the pressure, we'd end up producing more reactants. So it just depends, as I say, on the type of question. Here I've got an example before I move on to spec 7. So here you've got mentions in industry, some information at the top about ethanol, and you've got two reactants, and then you've got your products. And it talks about increasing the temperature. Now, firstly, we need to look at the fact that the forward reaction is exothermic and the backward reaction is endothermic. So we've got that information. I've got that from this sentence here. So it says the forward reaction is exothermic. I would say that's fairly important. Use Le Chatelier's principle to predict the effect of increasing the temperature on the amount of ethanol. Give your reason for your prediction. So again, we need to locate which one is ethanol. So look in here, it's got an 08. This is the one that we're focusing on. So there's your ethanol. If we're increasing the temperature, which reaction is going to benefit? So forward one's exo, that's got lots of energy, it's releasing it to the surroundings. The backward one absorbs energy from the surroundings, so therefore the backward one is going to benefit from increasing the temperature. So if it's going backwards, we're going to produce more of these on this side. On the left-hand side, we're going to produce more of the reactants. So therefore, when it says predict the amount produced, we would say it decreases because it's going to the left. And what you then need to say is a reason. So it says give a reason. So I would say the backward reaction is endothermic. If you said the forward reaction is exothermic, that'd also be acceptable, but I would pick the one that it's going to be following for that one, and that would be endothermic. Okay, so that pretty much brings to an end spec 6 in terms of information. What I would just like to mention is go back and I'm not going to go into too much detail on required practicals, but just bear in mind you have got 2 for spec 6. So in terms of your required practicals, I'll whiz through these. So here you've got the one with magnesium and acid. Here you've got the sodium thiosulfate one. So this first one is where you're catching the gas being produced in either a gas syringe or a measuring cylinder filled with water. Now I'm not going to draw any diagrams or go through the method in terms of writing it down, but I will speak it. So what you have is you've got some different concentrations. So you've got different concentrations of an acid. Now we used hydrochloric, but they could give you nitric, they could give you sulfuric, they might change it. So just bear that in mind. We reacted it with magnesium. Now, this type of required practical, it's all around the variables. So the variables are something they could ask you about. So the independent variable, the thing we're changing, is the different concentrations of acid. What are we measuring? We're measuring the amount of gas. It's all to do with measuring, said amount, naughty. So measuring volume of gas. every 10 seconds. And then also thinking about what you would control. So you'd control the mass of your magnesium, you'd control the volume of acid that you were using each time. So you might use 1 molar and 2, just depending. They could change that though. They could change that practical and give you different reactants, but it'd be the same principle. The sodium thiosulfate one is again a variables or method related question. So they could ask you either. Now what I would say is this came up on Separates last year. This one came up on Trilogy. So what I think could happen is they could switch. So this could be the Trilogy question. This could be the Separates question. So just bear that in mind. So for the variables for this, what are we changing? Again, we changed the concentration. So we diluted it. We made some dilutions. We created 5 actually. We did this in year 10. What did we measure? We measured how long it takes for the X to disappear. So if you remember, we had a conical flask. Underneath it, you had a tile with an X on it. And you're waiting for the moment that you can no longer see that X. And you would measure the time it would take for that X to disappear. So that would be your variables. Your method would purely be how you would set up that practical. So, Spec 7. It shouldn't take too long to go through Spec 7. So firstly, you just need to know some simple definitions. So we've got hydrocarbon. These things come from crude oil. So hydrocarbon contains hydrogen and carbon only. Keyword only there. Atoms only. 2 marker usually. You get a mark for saying that bit, you get a mark for saying only. So that's a hydrocarbon. Now these things come from or are found in crude oil, which is found underground, and it's the remains of dead animals and plants or dead organisms that have been trapped in rock, and it takes millions of years to form. They sometimes ask a little 1 marker, how long does it take for crude oil to form? Millions of years. But ultimately what we're wanting to get to are these hydrocarbons. Now, a type of hydrocarbon is an alkane. So an alkane's general formula would be CnH2n plus 2. There are 4 which you need to remember. So if you remember, monkeys eat peanut butter, so that gives you methane, ethane, propane and butane. You do need to remember the formula for each of these. So that beginning letter, monkeys eat peanut butter, is telling you how many carbons. So we're talking 1 carbon, 2 carbons, 3 carbons, 4 carbons. I'll pick propane as an example. So if I know monkeys eat peanuts, so I'm on 3, so it's got 3 carbons, put that into the formula. Whatever this is, we multiply by 2 to get 6, add 2, we've got 8. So that would be an example of an alkane. So that's hydrocarbons and alkanes in a nutshell. We've also then got fractional distillation, which is where we can start to separate out some of these different alkanes. Now this is done in a fractionating column. So you've got lots of different outlets for this. And what happens is the crude oil is heated up and it goes into the chamber. Now it's heated up. You get a mark for saying heated up on a 6 marker. You'd also say that you could say it's vaporized. And what happens is the crude oil starts to rise up the column. So 6 mark question, crude oil is vaporized. It's heated up and vaporized, rises up the column. What you would then say is that crude oil starts to condense, so it's evaporated in here. You then start to say it then condenses dependent on the boiling point. So a really important point is boiling point. I'll just put a little subheading. So we know if we're replaying this that we're talking about fractional distillation. I realise I've not written that down. Fractional distillation. So it's really what the important property we're talking about here is boiling point. Different fractions have different boiling points, so therefore they condense at different stages of the column. So at the bottom you've got things like bitumen. At the top you've got things like gases. If you remember, God puts naughty kids down females bogs. That gives you an idea of where they sit. So then we've got God, gas, puts, petrol, naughty, naphtha, kids, kerosene, down, diesel, females, fuel oil, and then bitumen, which is your box. So give you an idea of what's happening inside your fractionating column. If the question says explain why they condense at different stages, firstly you'd say they've got different boiling points, but it's to do with the chain length. So for example, if you've got a chain like that, which this would be ethene, and you've only got a couple of carbons in there with a few hydrogens around the outside, there's only going to be so many forces between that and another molecule of ethene. Whereas, for example, the lower ones down, which are really long chains, and we're talking, lots and lots of carbons. I could keep on going with this. I could go much longer than that one that I've drawn. They would have much greater forces. So therefore, because there's greater forces, it's going to mean that you're going to need a higher temperature in order to get them to boil. So that is the reason that they sit where they do in the fractionating column. So that's one technique. Now this is a separating technique. So it doesn't cause a physical change, it's just a separation technique. So it just causes a physical change. For one of your chemical changes that you need to be aware of is cracking, and I'll come on to that fact at the end. Now, each of these different fractions have all got different properties. So I would say, firstly, is you've got boiling point. We've discussed boiling point, and that's dependent on the length of the chain. So the longer the chain, the longer the boiling point. You also need to be aware of flammability. So flammability, how easy it is to ignite one of these. And a good example is petrol and diesel engines. So petrol in cars is ignited via a spark, whereas in diesel it ignites under compression. So it's actually quite difficult to light diesel in comparison to petrol. So as you go down the column, they get less flammable. Another one is volatility. So volatility is how easy it is for the fraction to turn into a gas. So again, as you go down, it gets harder for them to turn into a gas. You've got viscosity, which is to do with thickness. So the lower down you go on your fractionating column, the thicker the substance it will be. Something that I've just thought of that might help you work out what sits in the fractionating column. So if you remember long, bottom, high, and then the reverse is true for the top. So long chains, like this one, are at the bottom of the column because they've got high boiling points. So at the top, up here, we've got short, top, low. But I think long, bottom, high is easy. It rolls off the tongue, and it'll give you an idea of what sort of chains fit where in the fractionating column. I would say this didn't come up last year. It came up in terms of a one-word answer. What is this diagram? And separates, I don't remember it coming up at all. So I think they could ask a 4 to 6 mark question on fractional distillation. And then final little bit of information for Spec 7. Managed to get it all on one sheet. We've got cracking. Now the reason we do cracking is all to do with demand. So we don't need as much bitumen as we need petrol, as we all know, with loads of cars knocking about. So we need quite a lot of petrol, we need some of the shorter chains, but we're producing more of the longer chains that we don't necessarily have a high demand for. So what we will do is we'll perform this process called cracking. Now this is thermal decomposition. So what that means is we're breaking something down, decomposes via heat. So thermal decomposition. You take a long alkane, and you produce two things. A shorter one, so you get a shorter alkane, and you also get an alkene. I'll flip over to just show you alkenes in a second. So they're long alkanes, and you turn them into shorter alkanes and an alkene. There are two types of this. You've got steam cracking and catalytic. You might think, oh, I'm not sure about these. Steam uses steam, catalytic uses a catalyst. It's as simple as that, and that's all you need to remember. Final thing, for Spec 7, I'll have to bang another sheet on, but for Spec 7, the final point you've got alkenes, Make this nice and big. For this, you need to remember the general formula. So this time it's CnH2n. And alkenes have a double bond. So an alkane only has single bonds, so it would be classed as a saturated hydrocarbon. This one you would class as unsaturated. And the reason it's unsaturated is because it has that double bond in the centre. So there's the structure. For that, you can't have methane because it only has one carbon. So you're talking about ethene, propene, and butene as 3 to bear in mind. If it says ene on the end, then you know it's because it's got this double bond. If it says ane on the end, then you know it's because it's an alkane and it's only got single bonds. So just bear that in mind. So here would be a saturated one because the carbons are all making 4 bonds to different atoms. This one, it's got a double bond to another atom, so it's unsaturated, it's an alkene. And that is it for spec 7. So I'm going to pass over to Mr. McDade, who's going to whiz you through spec 8. Oh, a test for an alkene is the bromine test. And you get a brown. Oh. I thought you were writing something else. You get a brown colour with bromine. That's the test for alkenes. I think that came up a couple of years ago, actually, and Mr. McDade used to be a marker, and I remember him mentioning the fact that students couldn't remember the colour and also the test for alkenes. So we're going to have a 2-minute break in between, and then we'll start with spec 8.
Okay, so here we go with spec 8. So first of all, we're going to start off by looking at a couple of definitions. Okay, so first of all, we've got a mixture, which is 2 or more substances. Okay, now these are a mixture because they can be separated. Now, some definitions to think about when we're looking at this is that we have 2 definitions of the word pure. Definition number 1 is the scientific definition. So these, after they've been separated, are pure. And the reason that these are pure is because they are a single element or compound. And then we have the everyday definition of the word pure. You're expected to know both of these definitions, and the everyday definition is a substance that has nothing added to it. So just a couple of examples of that. If you have some pure gold, it only has gold atoms in it, so it is an element. If you have some milk, the milk is pure because it has come from the cow, it has been bottled, but nothing has been added to the milk between leaving the cow and getting to you when you open the bottle. Now, just moving on from purity, we now look at another definition, and the definition we need to understand about substances is what happens when we make a formulation. Now, the definition of a formulation is a mixture designed for a purpose, and that will have particular properties. Now, one of the examples I used when I taught this in school was we looked at a video about how lipsticks were made. Now, if you look at how lipsticks are made, they are a mixture of wax, pigments to give them their colour, and oils. Okay, in certain percentages. The reason they are made in a particular way is because you need a particular colour, a particular melting point, and you don't want the lipstick to be too brittle or too soft. If you get the formulation wrong, so the wrong percentages, the lipstick will not behave in the way it is designed to. A little bit of a more serious application of formulations is medicines. And if you look here, the tablet has 500 milligrams of paracetamol in each tablet. So it's vital that you get exactly 500 milligrams so people get the correct dose each time. Okay. Now, moving on from mixtures, the next logical step is to look at some methods, or one method in particular we use to separate mixtures. And that will be one of the required practicals, which is chromatography. So just to point out some of the really important points is that we have a pencil line drawn on the chromatography paper, and very, very important is the level of the solvent. Okay, where should the level be? The level is below the coloured spots. Now, just to take you through the required practical, the first thing you will do is you will draw a pencil line, a couple of centimetres above the bottom of the paper. You will then put ink dots on the pencil line. Following that, you would put the solvent, which is usually water. Don't be surprised if you get an example where it isn't water, in the bottom of a beaker. Okay, number 4 is you make sure the depth is less than the height of the dots. Okay, the next thing you will do is you will hang the paper in the solvent. We've usually done that with a wooden splint just across the top of the paper. Okay, so the bottom touches the solvent, right? And number 6 is you leave for the solvent to rise close to the top of the paper. Okay, that is the main 6 points about how to carry out the practical. There you can add a couple of extra points in a second, explaining what you would then do. Okay, so just to make sure you know those 6 points. Okay, please make sure that you look at the questions, because they will either A, ask you to describe how to carry out the practical, and don't be confused with B, describe how chromatography works. Okay, which we'll come back to in a little while. So once you have set up your chromatography and you have allowed the solvent to rise up the paper, the next thing you will do is you will then calculate an RF value. So the first thing you do is you will take your ruler and we'll do the blue dot, and I usually recommend you measure to the middle of the dot, okay, and that dot there has moved 50 millimeters, all right, and then you would measure how far your solvent has traveled. So let's just say the solvent has traveled all the way up to the top here, right? So if that was what I am measuring, we have got 86 millimeters. Now your RF value is the distance the spot travels divided by the distance the solvent travels. So you would do 50 divided by 86, which will give you an answer. Your answer will always be between 0 and 1, because you are dividing a small number by a big number. If it isn't, the chances are you have just done these two the wrong way around, so you can use that to check whether you've got the correct answer. Now, just going back to what we mentioned on the previous page is how it works. Okay, so first of all, we have a stationary phase. That's the paper. It doesn't move. Then we have a mobile phase. That is the solvent. So what happens is the solvent rises up the paper. As it rises, it dissolves it could be inks or colorings. Right? The more soluble the ink is, the faster it will rise up the paper. Okay, so we end up with the most soluble at the top and the least soluble at the bottom. Okay, just one final thing. You get really nice questions where there's loads of options for the next answer, which is just to say what this called a chromatogram tells you. Well, first of all, it tells us that our brown ink is a mixture. Then it tells us that our red and our blue are pure. The brown ink is a mixture because it has been separated into more than one colour. There's lots of options for questions like this. We could also say that the brown ink contains the red ink, and the brown ink contains the blue ink, and the brown ink contains the yellow ink. Just look out for one other thing. If you still have a dot on your pencil line, got a pencil line, I forgot to say that earlier, because the pencil is insoluble, it won't rise up the paper. If you still have a dot at the end, that means whatever this is is not currently soluble in the solvent that you are using. Okay, so an example of that would be if you'd used a permanent marker, the water isn't going to dissolve it and it isn't going to rise up the paper, so you would use a different sort of solvent to investigate it. Okay, so that is your required practical and how to analyse a chromatogram. We're going to move on to something that's really worth learning, and it doesn't take too long, and that is how we analyse substances which are gases to work out what the gas is. So all of these gases on here look pretty similar. You won't be able to tell any difference by looking at the bubbles. Okay, so how do we identify? Let's start off with hydrogen. So let's just start off with hydrogen. We will take our test tube with oxygen in it, and inside it we will put just a glowing splint. So we've blown out the splint, and a glowing splint relights. Okay, our hydrogen, same again. We will take a test tube of hydrogen, and this time we would put not a glowing splint this time, but we would take a lit splint. Okay, and this would set fire to the hydrogen, and we get a very distinctive squeaky pop from a lit splint. Okay, the next one, chlorine. Okay, so same again. We have our test tube full of chlorine, and we would take some blue litmus paper, okay, which is damp, right? This would happen in 2 stages. The first thing is the chlorine gas would turn the blue litmus paper red, and then it would turn the blue litmus paper white. Okay, so this is damp blue litmus, and it is white because it has been bleached by the chlorine. And finally, carbon dioxide. One of the most common wrong answers, because people get a little bit confused and they talk about splints, is that it extinguishes a splint. No, because there's lots of gases, particularly nitrogen, which is more than 3/4 of the air, which would also extinguish a splint. So what do we do? Well, what usually happens is you might see this done in 2 stages. You've got your reaction, and it's producing bubbles. And what you can do is you can take a pipette, and you literally suck the gas from above the reaction. And then you take your pipette, which you suspect might have carbon dioxide in it, you put it in another test tube, and inside that test tube we have lime water. Okay? And if carbon dioxide is present, when you squirt the carbon dioxide into the lime water, it will turn the lime water milky or cloudy. Okay, so there's your 4 gas tests. Mr. Addy has already mentioned that you need to learn your test for alkenes, which is they will turn bromine water from brown to colourless. There's just one other extra thing I think I might pop in because we've got time, and it isn't a liquid, is how do you confirm that a liquid is water? Well, water does something really, really special, and it will turn blue cobalt chloride paper a very nice, obvious pink. Water is the only substance that will do that, so that's a really specific and really clear test. Okay, so now we are going to move on from spec 8 to spec 9, and we are going to have a look at the Earth's atmosphere. Okay, so first of all, what you have to be really aware of is that we are looking at two things. We are looking at what the early atmosphere used to be like and how it compares with today's atmosphere. So on a foundation paper, I'd expect questions where you just have to compare the two. Okay, don't forget comparing is what is similar and what is different. Okay, so we can see that originally, billions of years ago, the Earth's atmosphere is mainly carbon dioxide. There's a little bit of water and other gases. Right, now this is very similar, okay, to Mars now. Okay, so you get questions written by examiners where they ask you to compare today's atmosphere with Mars's atmosphere. It's no different. You're just looking at the two pie charts. So the next thing that we need to think about is this. How did this happen? Well, I'm going to tell you that you need to tell a story. This is a very, very common 6-mark question. Okay, last year's exam paper, they asked you specifically to state how carbon dioxide levels had decreased, and oxygen levels had increased. Okay, so let's just think about what happens here. So originally, the Earth's surface was very hot. Okay, it was covered in molten lava. So the next thing that happened was the Earth cooled. Now, because the Earth cooled, the water vapor in the atmosphere condensed. This caused lots of rain, and this produced the oceans. Okay? Because the water vapor condensed, the water vapor was a really high degree of clouds. So what happened was, because there were less clouds, there was more sunlight. Now, because we've got more sunlight, and we've got the oceans, okay, primitive plants evolved. Now, we all know that these primitive plants evolved further into more complex plants. Now, because we've now got plants, the next thing that could happen is that photosynthesis takes in carbon dioxide and turns it into oxygen. So the carbon dioxide levels start to go down and the oxygen levels start to go up. Okay? Now, lots of other things go on at the same time. What also happened is that the oceans dissolve carbon dioxide. So that also meant the carbon dioxide levels went down. What then happened is that we ended up with oxygen levels increasing, so animal life now evolved. Okay, animal life evolved. Animals respire, they take in oxygen, and they release carbon dioxide. Okay. Now, what also happens at the same time is that the remains of dead organisms turn into fossil fuels and limestone. and other things like peat. Now, these are known as carbon sinks, and they make the carbon dioxide levels also go down, right? So if you notice on there, we've got lots of different things happening that made carbon dioxide levels decrease from 95%. And then we ended up with a situation where plants were photosynthesizing and animal life was evolving and respiring at the same time. And that meant that the carbon dioxide levels and oxygen levels stayed at a very, very steady percentage for the last few million years. Okay, so make sure that you can take an examiner through all of the steps explaining what happens. Okay, don't forget to mention that that is respiration. Okay, now, next thing, we're going to talk to you about the greenhouse effect. Now, first of all, what you need to know is that the greenhouse effect is natural. Okay, man did not create the greenhouse effect. Now, what happens is that ultraviolet radiation from the sun warms up the surface of the earth. The warm surface of the earth emits infrared radiation, which on somewhere like Mercury would just go all the way back into space. But what happens on Earth, because of the carbon dioxide in the atmosphere, is that gets absorbed and doesn't even leave the atmosphere, or it even gets reflected back. Okay? So infrared radiation is absorbed by carbon dioxide and methane and water vapor. Okay? With methane actually being one of the worst greenhouse gases. Now, up until about 300 years ago, the greenhouse effect, we had a 0.03% carbon dioxide in the atmosphere. But what has happened is that there has been an increase in greenhouse gases. Okay, there has been an increase in CO2 because of the combustion of fossil fuels. There has been an increase in CO2 because of deforestation. Okay? There has been an increase in methane in the atmosphere from farmed animals. And what people don't realise is the main culprit is rice growing. Okay, rice growing in paddy fields produces way more methane than farmed animals. Okay, so we've got an imbalance now. Okay, because what we did have at one point was that carbon dioxide was reacting with water during photosynthesis to make the glucose and the oxygen. And at the same time, this process was reversed during respiration, and we had a nice steady balance. And you will have come across this in biology when you've looked at the carbon cycle, okay? But what has happened is we have started adding more CO2 from the combustion of fossil fuels and deforestation. We don't actually add carbon dioxide by deforestation, we just slow down how fast we can take it back out of the atmosphere. Okay, so carbon dioxide percentages have gone up from 0.03% to almost 0.04%. All right, So we've got a much higher percentage of greenhouse gases in the atmosphere absorbing that radiation. So this means that we end up with a phenomenon which is referred to scientifically as global climate change. Okay? Now, lots of people say that the greenhouse effect causes global warming. Well, yes, it does. But global warming is only one of the consequences of global climate change. So there's lots of other things. So we have melting ice caps and glaciers. Okay, what else do we have? We have loss of habitats. We have floods. We have droughts. We have more extreme weather. And yes, we have warming, and in some places in the world, cooling. Don't forget the melting of these ice caps and glaciers leads to rising sea levels. So all of these are consequences of man's effect on the environment. Okay, so it's not just global warming. Now, global warming, yes, overall, the average temperature is going up around the world. All right? But in some places it's going up, in some places it is going down. Right? Now, what's the next diagram? Well, the next diagram is your carbon footprint. Now, what is your carbon footprint? Your carbon footprint is your annual overall increase in CO2 levels. So it's what you personally add to the atmosphere every year. And you can see that there are lots and lots of different ways you do that. One of the worst culprits is flights, when you go on holiday. Okay? But it's everything that you do. It is things like transport, so the school bus. It's all those journeys you take. It's every time you switch something on, because that electricity is coming from a power station which is probably burning a fossil fuel. Okay? It is also things like your heating at home. Okay? Now, a couple of things that you can do that would counteract that is anything you possibly can do to reduce or recycle. Because, for example, if you make a Coke can out of recycled aluminium, it will use 90% less energy to make another Coke can rather than making new aluminium from iron ore. The other things you can do are things like you can offset your carbon by doing things like tree planting. Some airlines will ask you if you want to offset your carbon, and what they will do is they will charge you a few quid extra and they will plant some trees. Okay? So that's your carbon footprint. Now, the last part actually relates to something Mr. Addy mentioned. There's a link here between your hydrocarbons and this. So products of combustion, right? Now, we're going to look at combustion in two separate areas here. We can take carbon or coal, and we can burn it, and we can make carbon dioxide. Okay? Now, the second thing we can do is we can take a hydrocarbon, like methane, the gas you use at home, it comes out the gas taps at school. We can react that with oxygen as well. Okay? And you are going to make carbon dioxide, but because the hydrocarbon also has hydrogen atoms there, we will get some water formed. Okay, and I'll get a nice balanced equation there for you. So what's going on? Yeah. So again, look at what we've got here. We've got 2 greenhouse gases. We don't worry too much about the water vapour, okay, but the carbon dioxide and the water are both greenhouse gases. Now, there's also a little bit of a problem here, is that all fossil fuels contain a little bit of sulfur. Sulfur reacts with oxygen to form sulfur dioxide. That can turn into sulfur trioxide in the atmosphere, SO3, and that is responsible for acid rain. Okay, then we've got one other equation to think about, and it is this, right? We can take our nitrogen from the air, which ends up in car engines, with the oxygen from the air. This makes all sorts of different gases, things like nitrogen dioxide, nitrogen monoxide, okay, NO, N2O, NO2, all right? Now the NO2 in particular, there's another one, acid rain. These are bad for your lungs. They give you respiratory problems. Respiratory problems. I think I spelled it right. Okay, so there are the 4 main reactions. I just want to go back to the top ones, okay? Because if you take something like methane and you don't provide it with enough oxygen, you will make carbon monoxide and water. Okay? All right, I think, if I get this right, we'll get a balanced equation. There's something like that. Okay? I think that's right. Might be wrong. 3, 4 of them. Okay? So carbon monoxide. Okay, Mr. Addy will correct me if I've got that one wrong. Now the carbon monoxide, because we've not got enough oxygen, is toxic. Yeah? It destroys or makes useless your red blood cells. Right? Okay? So this is because we have incomplete combustion, right? Not complete combustion, right? So there's not been enough oxygen. That's why it's important that you get your boiler serviced every year. So just go through that again. Carbon dioxide and water are greenhouse gases. We've got gases that cause acid rain and carbon monoxide. Just be careful when you're talking about products of combustion, right? You need to be specific about what sort of pollution they are causing. Is it a greenhouse gas? Is it acid rain? Right? Now, moving on. We are now on to Spec 10, I believe, Mr. Addy. Is that right? Now, so, first of all, we've got a definition that you need to know. We are going to talk about potable water now. Potable water is very straightforward. It is safe to drink. Okay? So most of the world's water is not potable. Okay? The water in the sea is not potable. The water in reservoirs is not potable. The only water which tends to be potable is groundwater or spring water, which has been filtered as it passes through rocks. So we've got to think about, okay, drinking water. How do we make that water safe to drink? And I also want you to be very clear that there is no connection whatsoever between the treatment of drinking water and the treatment of wastewater. So drinking water, so the water that comes from the reservoir. What do we do first? We have to screen that water. Why do we screen it? To remove large debris. So that could be stuff like twigs, plastic bags, anything. Okay, pebbles. The next thing we do, it is filtered through fine sand. It's actually filtered through sand a few times, and the sand grains get smaller and smaller each time, so it removes more and more and more of the insoluble stuff like grit and stuff like that. And then finally, once we've got rid of all the dissolved solids, we have to then disinfect with chlorine. And that is to kill the bacteria. Okay. Now, in some places in the world, they don't have lakes and reservoirs because it is too dry. But they are surrounded by lots of undrinkable seawater. So we have to go through a process called desalination. Now, there's two ways we can go through desalination. Number one is we can distill the salty water, okay, and that will leave behind the solid salt, and you will collect the steam and you will condense the pure water. The only problem with that is it is very slow and it uses lots of energy. Okay, and the second way we can do this is something called reverse osmosis. So normally what would happen in osmosis is that the salt particles would move from an area of high concentration to an area of low concentration. Okay, we don't want that to happen. We want to leave the salt particles behind. Okay, so what happens is the concentration of salty water builds up behind a membrane, and on the other side of the membrane we end up with water with a very, very low concentration of water particles. It goes through a semi-permeable membrane, lots of pressure, and what happens in this instance as well is the water particles are much smaller than the salt particles which get left behind. Okay. Now the next thing is what do we do with wastewater? So wastewater is everything that goes down your toilet, your sinks at home, when you wash your clothes, but also it is the rainwater that runs off the road as well, and water that runs off farmers' fields, and that some of it can end up in the drains, and that gets sent off to the water company. So what's the first thing that happens? So the first thing that happens with this dirty water, again, we need to screen it. Okay, that basically, again, goes through a large gauze, like a cage. It traps all the big bits. The next thing that needs to happen is that we need to go through a process of settlement. Okay, so what happens is the water is literally just left. Okay, so the particles sink to the bottom of a tank, and then they pump the water from the top of the tank. Now, the next thing is digestion. So in this water now, we've got loads of what's called organic material. Okay, so that's the waste food that leaves your body when you go to the toilet. Okay, and it's organic material. Digestion can either be aerobic. So what they do is they put in giant tanks with bacteria, bubble loads of air through it, and the bacteria literally digests and feeds on the organic waste. They then put it in a sealed tank for a second stage of anaerobic respiration, where the bacteria again feeds on more organic waste. Okay, now that that's happened, we've taken out the large bits, the small bits, and we've taken out lots of the organic material, and then that is now clean enough to return to the river. Okay, that water now goes into the sea, where it will evaporate, it will rain somewhere else, and it will go all the way back around the water cycle to fill up the reservoir and the lakes, where it will then be used to turn into clean drinking water. Okay. Got 3 more things left from me. This one's not going to take too long. So what we are now looking at here is how do we go through a life cycle assessment. Okay, well, we're going to go through it in 4 stages. Okay, so first of all, extraction of the raw materials. So, mining, crude oil. Okay, this affects habitats. It causes pollution because you have ships and lorries and machinery. The next step is the manufacture of an object or product. This is done in a factory, which will use energy. It produces waste. It may use lots of water. Okay? So again, it has an impact on the environment. Extraction has an impact on the environment. The third stage of a life cycle assessment is the use of what you have made. Okay, so for example, this pen, we don't worry too much about that stage because during its use, this pen's not really having much of an effect on the environment. But it might be something that needs chemicals, like detergents. It might use lots of water, like your washing machine. It might use loads of electricity. It might be noisy. Electricity causes pollution. And then finally, when the object gets to the end of its life, it needs to be disposed of. So, is it biodegradable? So can you just happily bury it under the ground? Or will it end up as landfill and sit there for thousands of years? Can you reuse it? Can you recycle it? But also, can you burn it for energy? Okay, gone through that pretty quickly. Went through it so quickly, I forgot to mention one of the most important ones about the extraction. Are you extracting something renewable or non-renewable? Okay, because that has a massive impact on the environment. Last year there was a question about this on the exam, and what you were asked to do as an examiner was to actually assess whether all 4 areas had been addressed. Okay, I think I'm going to skip the model question from last year and move on to the very, very final part of what I'm going to be doing this evening. Now, this is higher only. Now, these are biological methods of metal extraction. Why? Because we are running out of high-grade ores. Okay, so there are 2 methods of metal extraction that you need to know about. Number 1 is something called phytomining. How does it work? Very straightforward. You grow plants. Specific plants that absorb metal ions from the ground. So particularly useful in areas where the percentage is low, because all the high-grade ores have been used up for certain metals by the mining companies. The next thing you do is you harvest the plant and you literally burn it. Okay? You then dissolve the ash, and then you use electrolysis or displacement to extract the metal. So by displacement, I mean if you've got a more reactive metal, you can put loads of scrap of that metal in, and it will displace the less reactive metal. So for example, for copper, you could displace it with scrap iron. Okay. The next one is bioleaching. What is bioleaching? Bioleaching is you use bacteria to absorb the metal ions. This is good because bacteria multiply. What do you do next with the bacteria? You break it open and you have a solution of metal ions. Finally, same stage as the last one, right? So you use electrolysis or displacement. And remember, this is higher only. Okay, so that is the end for everybody who's doing Trilogy. We're going to have a quick break, and then Mr. Addy's going to come back and he's going to do the extra stuff for separate sciences.
Okay, back with me. I'm going to take you through the separates content for paper 2. There isn't a great deal, to be honest. I'll start with spec 7. There isn't any for spec 6. Straight in with alkenes. We're going to look at all the functional groups that you need to know for spec 7. So first one being alkenes. Just remembering that you're getting this from cracking. So you're cracking a longer chain alkane. It's a cracking process. You then get a shorter chain alkane and you get the alkene. And just remember that it is unsaturated. Just a bit of a recap there. Now, alkenes, remember it's a carbon-to-carbon double bond. And then there's some reactions that you need to know for some of these. Now, I've already talked about alkenes and the general formula earlier on. So if you're unsure of that, check it out. Some reactions that you've got. So firstly, you've got alkenes reacting with hydrogen. Now, think about it. What you're basically doing is you're adding extra hydrogen to this. All it's going to do is it's going to produce an alkane. So depending on the alkene going in there, so you might have something like ethene, add some hydrogen, you're going to end up with ethane. Then you've got alkenes reacting with a halogen. So I'm just going to pick bromine as an example. If I react these, what you then end up with is you end up with something that looks like this. So you add these on, so there you've got your bromines. So there you've got your new structure. Now this time what's happened is the bromine has then bonded. Now this is the reason for the bromine test, whereby you start off with something that's brown and it then turns colourless, because this is what is happening chemically. So I just wanted to recap that, because I realised at the end it was perhaps not totally clear. Again, a different halogen this time. So if you had chlorine, you get exactly the same thing. It's just this time, instead of bromine, you end up with your chlorine on there. And the final one, you've got your alkenes reacting with water in the form of steam. And when you do that, you produce an alcohol. So in this case, we've got ethanol being produced. Just as an example. So there we go. So there you can see you've now made an alcohol because of that functional group. Functional group of an alkene is your carbon-to-carbon double bond. So there we go. I'll chuck on the general formula as well, but as a recap. So CN, H2N, dead easy. Alcohols. So functional group this time we're thinking about is the OH group on there. See that? You know it's an alcohol. Alcohols asked quite a fair bit last year, so in terms of predictions, I don't think they'll come up as heavily as they did last year. There were quite a lot of questions on it on separates around alcohols and fermentation. So firstly, thinking about some of the reactions that these things have. You can dissolve them in water. If you do that, then you get a neutral solution. So you take your alcohol, dissolve it into water, so you get something that's neutral. You can react them with sodium. If you react them with sodium, you produce hydrogen gas. So our hydrogen produced. So there's another reaction. You can burn them. Now, if you're burning them, it's just combustion. So you're burning them in oxygen, aren't you? If you're burning them in air, it's the oxygen they're reacting with. And in that case, if it's a combustion, then it sort of becomes a combustion reaction almost. You then get in carbon dioxide and water produced. You can react them with carboxylic acids, and we'll come on to what the functional group for these is in a second. Let's just get these little things underlined. So react with carboxylic acids. And these make esters. You can also oxidize them. So if they're oxidized, again, you get, this time, you get a carboxylic acid produced. Because if you think about it, you're adding oxygen. So to that carbon, you're then getting an oxygen bonded. Carboxylic acids produced. So they're your reactions of alcohols. Like I said, there's also fermentation. There was a 3-marker on separates on fermentation last year. So I'm not saying it's not going to come up, but it's unlikely because it's a small little topic on there. I think it's going to go on, be on one of the other functional groups, to be honest with you. So carboxylic acids, functional group, COOH. That would look like this. So you've got a carbon double bond to an oxygen and a single bond onto that hydroxyl group, this OH group here. So these are weak acids. So in comparison to things like hydrochloric acid, which would be a strong acid, these only partially dissociate into the ions. So that's where that term weak acid. So a bit of paper 1 spec 4 stuff coming into it, because it's important. So for carboxylic acids, you can dissolve these into water. And if you do that, you get an acidic solution. You can also react them with carbonates. Now remember, it's an acid still. Even though it's a weak acid, it's still an acid. So if you react these with a carbonate, you're going to get carbon dioxide being produced. So react with a carbonate, you get CO2 produced. You can also react them with alcohols. And in that case, you then get an ester. So I would say that they're your main 3 functional groups, really, for Spec 7, the additional ones. Like I said, alcohols asked a lot last year, so it could be one of these 2. You've then also got polymers, which didn't figure heavily, really, to be fair, last year. So two types of polymer. Polymerization, sorry. You've got addition, which is nice and easy. This actually crops up a little bit on paper 1 in polymers. So addition polymerization, it's where you take something like ethene. So you take something like ethene, and what you're wanting to do is break open that double bond. So in breaking open that double bond, what you then do is you create something with just a carbon-to-carbon single bond. Then, because you've broken open this bond, each carbon is making 4 bonds. So 1, 2, 3, 4. This one, 1, 2, 3, 4. So these want to make 4 bonds as well. They were already bonded to 2 hydrogens, so that spare bond is going to be dangling out over there. Same goes for the one on the right. What we then do is, instead of writing out this massive chain, because addition polymerization is all about producing some polymers, which can be used in things like polythene, so that'd be plastic bags. So these chains are really, really long. And to save you time, instead of writing them all out, which would take you years, you can do the repeating unit, which is just those 2. You put brackets around it and an N. And that's addition polymerization, because you're adding these things together. Whereas condensation, the other type of polymerization, they asked a little 1 marker on this last year, whereby they asked you what small molecule is produced during condensation polymerization. So for this time, this has got 1 functional group. For condensation, I'm not going to draw an example because it'll take a bit of time, and I understand we're a bit behind. So this is where you have 2 functional groups. So you've got different examples where you might have 1 functional group on one and another on another, and therefore that then creates a slightly different polymer. So you end up with polyester. So you get a polyester, and you also produce water. And then also for Spec 7, you've also got a bit of DNA and amino acids. Oops. Knock my pens over. So DNA and amino acids. So an amino acid. The important bit about it is it's got 2 functional groups. So it has an amine group. So I'm going to put 2 func groups. It's got an amine group, and it's also got a carboxylic acid group as well, which is quite interesting. So these can polymerize, and therefore what happens then is you then polymerize in together to produce a polypeptide. So when it polymerizes, you get a polypeptide forming, and then when you've got different amino acids polymerizing, a protein forms. So it just gives you an idea really of how proteins are built up. And also linking it to your amino acid. So this stuff is linked to it's a type of polymerization, if you like. So you're producing polypeptides. So from these, you get polypeptides. I'm not going to write everything down, as I say, because, again, it is just a bit of extra information that I'm talking to you, so I don't want to write all the definitions down. And then you've got DNA, which stands for deoxyribose nucleic acid. So that's where this DNA comes from, if you weren't sure. And it's a double helix. So you've got this sort of thing going on. and you've got these base pairs in between all of that. I'm sure you've seen these things, and you will have seen this in biology anyway. In DNA, it's a large molecule, and it's made up of different nucleotides. You've got A, T, C, and G. So what you find is that these two will bind together as will these two, and that's your DNA. You just need to know that you've got your amino acids, two functional groups, your amine and your carboxylic acid. They polymerize to make polypeptides, and you just need to understand the structure really of DNA. But I know that you've done that in biology, so I don't want to sort of go over that too much. So that is Spec 7. Then we've got a little bit of some testing on Spec 8. So I'll move on to Spec 8 now, and then we'll look at the stuff for Spec 10. Now, the good thing about Spec 8 is it's all based around some testing of different things. So Spec 8 is called chemical analysis. Now, you do chemical analysis because you're looking at pure substances, formulations, chromatography for separating as a separation technique. It also looks for tests for gases, which again is chemical analysis. Now, one of the first different chemical analysis techniques that you can use is a flame test. So flame test, there are 5 different ions that you need to remember the colour for. So you have lithium, sodium and potassium. You've also got 2 others which aren't in group 1. So you've got calcium, and you also have copper. So if you were to take any of these, what you would do is you take a nichrome loop, you dip it into your substance, your sample, could have one of these in it, and then you'd put it into the blue flame of a Bunsen burner, and depending on the colour that you see would determine the ion. That would help determine the ion that is present. So if you see a crimson flame, then you've got some lithium in there. If you see a yellow flame, then you have some sodium. If you see a lilac flame, you have potassium. Calcium is orange/red. I have seen some places refer to it as brick red, but you can say orange-red. And then copper is green. So they're your flame tests for each of those. I'll come on to, when I've got all the information on here, I'll then come on to how they could put this into an exam question, because it's one of my, not big predictions, but a minor prediction really for separates this year. Then again, another way of testing metals is the hydroxides test, which is where you're producing some precipitates, and that's reacting them with sodium hydroxide. So again, you're looking at different metals, reacting with that, and you would then get a different colour precipitate depending on the metal ion present. So there are 3 ones that have got a bit of colour to them. So you've got copper, iron 2, and iron 3. Copper produces a blue precipitate. Iron 2 produces a green precipitate. Iron 3 produces a brown precipitate. So they're the colourful ones. Then you've got 3 others. So then you've got calcium, magnesium, and aluminium. Now each of these produce a white precipitate. So that makes it nice and easy because they're all the same colour. I'll put on somewhere that these are precipitates, just so you're aware. However, the aluminium, if you were to keep on adding sodium hydroxide, it then redissolves, so it turns back colourless. So if you had these 6 out in front of you, and you could see the colours of these 3, but these 3 were all white, you then might be thinking, well, how do I know which one's which? If you carry on adding in sodium hydroxide, the aluminium eventually will redissolve and it'll turn colourless again. So you know that one would be aluminium. And then between calcium and magnesium, how would you determine that? Well, that's where you'd then use your flame test. So you'd then use the colour of calcium there, orange-red, to determine that. So the one left must therefore be magnesium. So there's your hydroxide test. They didn't come up at all last year. There were a couple of questions on certain colours for the flame test, but this didn't come up at all. Then you've got your non-metals. So you could say that these are your metal ions. And these are non-metal ions. So this time, one of them you've got is sulfates. You've also got carbonates. And you've got halides. Now sulfates, you're looking for SO4 in there. It's a 2- ion. Carbonates, you're looking for CO3 and a 2- ion. And your halides, chloride ions, bromide ions, and iodide ions. So they're the 5 non-metal ones that you could potentially be asked about. Pretty sure there was a question on it's either sulfates or carbonates last year, so it might swap round. So it's certainly worth remembering these. So for testing sulfate, what you do is you take some barium chloride and you add that along with hydrochloric acid. So there's two things you're adding in there. So hydrochloric acid, barium chloride, and if it's positive, you get a white precipitate. Next, you've got carbonates. So this time, what you need to do is you're probably going to add this to an acid. So you'd add an acid, any acid really. I would probably say a dilute acid actually. So you add a dilute acid, and that's therefore going to then produce some gas if it's got a carbonate present. So you try and catch the gas or channel it through a tube or something. And you'd want that to go into some lime water. And this comes on to something Mr. McDade talked about earlier around the test for gases. So if it is a carbonate, it is producing carbon dioxide. So therefore the lime water would turn cloudy. Halide test. So this involves two additional reactants you need to add in there. So you've got nitric acid and silver nitrate. So they're the two additional ones. This time if there's chloride ions present, it would go white. Bromide ions would go cream, and iodide ions would go yellow. So they progressively get in more colourful. Now, they did ask some questions on the flame test. I'm not going to go through flame emission spectroscopy because that was one of the first questions on the paper. So, and that is quite a straightforward question. It's just looking and lining them up really with a ruler. So I'm not going to go over that. But they did ask questions on certain ones of these and a couple of ones of these, but they didn't ask about hydroxides. They didn't ask about halides. I'm wondering whether they might give you a big 6 marker where you've got an unknown substance and they're wanting you to talk about all of these tests. So they would maybe give you a bit of information around the background of a compound or something, and then you'd actually be expected to talk about each of these tests, how you'd identify it. So if it was calcium, you'd have to go back and do a flame test, or if it was iron too, you'd have to, because obviously iron isn't going to be a flame test, it's going to be a hydroxide test. So just depending what compound they suggest to you, or it might be a complete unknown, you'd talk about all of these different things. I actually think that would be quite a nice question in a way, because you can just go at all these tests and there'll be loads of marks there to pick up. Now, finally on to Spec 10. So there isn't anything for Spec 9 in terms of separate, so we're then on to Spec 10. So hopefully not too behind now. So there are about probably 4 or 5 extra lessons for this topic, for this spec point rather. So you've got corrosion. Now in corrosion, there are really two sorts of types of ways of preventing it, because it's all around the prevention. So if something corrodes, it's been eaten away at, usually by the elements, as in the air, water, etc. And it's usually metals like iron, which are very susceptible to being rusted. So what we're wanting to do is wanting to come up with ways to stop, because iron is very useful, it's very strong, but as we say, it's susceptible to reacting with air and water, rusting. It then becomes brittle and it breaks off easy, and it's suddenly no good anymore. So what we're wanting to do is we're wanting to come up with ways that we can prevent that from happening. So there are 2 real routes, I would say, for this. One of them is sort of keeping it away from things like air and water. So what you might do is you might use electroplating, where you might electroplate a different metal on top of, let's say, iron, and therefore that would then stop it from reacting with air and water, etc. Another method would be using a more reactive metal. So you could use a more reactive metal. Now there are two routes for this one. One, you might have sacrificial, which is where you might have sacrificial metal, which would be more reactive. So an example would be using something like magnesium. So magnesium, if it was something you're trying to stop iron from rusting, magnesium would react with the water in the air first, so therefore it would be sacrificed, therefore protecting the iron underneath. Another one is galvanizing. Now they're not the same thing. Galvanizing is where you put on a barrier So you might have a barrier metal, it might be something like zinc, which again isn't as reactive as magnesium, so it's going to act more as a barrier. It's not going to react straight away with the water and the air. But if it got scratched and then did start to react, it would then still be sacrificial. So within galvanizing, you've got a bit of both. You've got a bit of a barrier and sacrificial, whereas for sacrificial, it's purely just reacting. Then you've got alloys, which is another topic. For this, it's really quite straightforward. It very much links to Spec 2 when you look at alloys and metals and how the layers don't really slide over each other. And ultimately, just having multiple metals makes something stronger. And that's what it all boils down to, really. And again, it rolls back to having the layers distorted in an alloy, meaning that the layers can't slide over each other, thus making the alloy stronger. In terms of another topic, so I think there's probably another 3 or 4. So composites. These are quite simply a mixture. And each individual component would have its own properties, but if you mix these together, these would then become stronger compared to the individual components. So there we go, that's all you really need to know around composites. Then you've got different types of different chains in terms of polymers again. So polymers comes back up again. I know we talked about polymers earlier, but I'm going to put polymers on again. So within these, you've got 2 different types of polymers. So you've got thermosoftening and thermosetting. Softening and thermosetting. So thermosoftening, what happens is if you heat these up, the intermolecular forces, are weakened, and therefore the chains slide. So these get weakened, and the chains slide. So hence the softer. Thermosetting have got something called cross links. And what that means is they don't soften, so they're set in place. So a couple of different examples of, they did actually ask a question right at the end of the paper on, I think it was thermosetting, why is this such and such? I can't remember what it was talking about, a plastic anyway, and it was on about thermosetting, I think. So that did actually come up last year. Then you've got 2 specific types of polythene that you need to be aware of. So you've got low density polythene and high density polythene. So just need to know that firstly these are made of polythene, but they are different types of polythene, and the reason that they exist is because they are produced at different temperatures and pressures. Whoops. And they also produced with different catalysts. And therefore it gives them different densities as previously mentioned. And then the final thing that we need to be aware of for spec 10, and right on the back of this exam question, just run out of paper. So as final thing for spec 10, or final 2 bits for spec 10 actually, you've got the Haber process and you've got fertilisers. So I'll do Haber on one side and then fertilisers on the other. For the Haber process, or Haber process, came up last year in a fairly big way actually. So they may ask you where you get the nitrogen and hydrogen from. So nitrogen comes from the air, hydrogen comes from a reaction with methane, and then you get the hydrogen. You need to, basically this is all around making ammonia. So what you have is nitrogen added to hydrogen, and you're producing ammonia. We then would balance it, so we've got 2 nitrogens, which stick a 2 there, which means I therefore then need a 3 in front of our hydrogen. So that's balanced. You need to know the conditions that this is done at. So it's done at 200 atmospheres of pressure, and it's done at 450 degrees. Now, this is a compromise. So, firstly, it's done at a decent enough temperature, high enough temperature to get the rate going, so the rate is fast enough. And it's also done at a certain pressure so that to maximise the amount of ammonia produced. Because obviously, if we increase the pressure, looking at this, using our equilibrium skills, we know if we increase the pressure on this reaction, it will move to the equilibrium and shift to the right, so therefore we will make more ammonia. But it costs a lot of money to increase the pressure, so there is a compromise on each of these two things there. Also uses an ion catalyst. So thinking back to spec 6, what is a catalyst? It reduces the activation energy, speeds up the reaction, provides an alternate pathway. During this, ammonia is constantly removed. So if we think about why they're constantly removing this, they're therefore reducing the concentration of ammonia. That therefore means that the concentration of this is higher, so equilibrium shifts to the right to produce more ammonia, keeping the reaction going. So that is why it's removed constantly. And it stops the reaction from going back the other way, which would obviously be very bad. What's also really good about the Haber process is that they recycle the nitrogen and hydrogen if it is unreacted. So any unreacted hydrogen and nitrogen is recycled. However, unfortunately, it doesn't always fully react. So that is one of the reasons that they recycle it. So that's your Haber process in a nutshell. I've not spent a long time on that because, as I say, it came up, I think it's like a 4-mark question followed by a few questions on it. So it's more likely it'll be a different, separate question that we'll ask. Fertilizers then. So you just need to know about NPK fertilizers. So you've got nitrates, phosphates, and potassium ions. Potassium, we'll put. So potassium. So the phosphate ones, they're of interest really. They react with acids. And what you can then produce are some soluble compounds, because phosphates on their own are generally insoluble. So therefore, if you think about that logically, if you're wanting to put these in the ground to make something grow and they're not soluble, then they're not going to dissolve, not going to work very well. So it's not going to get into the soil so that the plant can take them up through the roots. So what we have to do is turn them into something soluble first. So there are a few reactions. I'm just going to write them out and then we're done. So you get some phosphate rock. What you can do is add that to 3 different acids. So you've got nitric. You could add it to sulfuric. I'm not going to write acid on, because hopefully we should be aware that we talk about acids by now. Or phosphoric. So all of these different acids. This one, you're going to get phosphoric acid and calcium nitrate. This one is calcium phosphate and calcium sulfate. And this one you've got calcium phosphate. The top one, you can then add that to ammonia and you make ammonium. I'm just going to put am phosphate. Quite a small topic, fertilizers, though, to be honest. It's mainly around why you might want to dissolve. I would imagine they could ask a question on why would you want to make them into something soluble, and then you could talk about how they're insoluble, so you have to turn them into these soluble compounds by reacting them with acids, and therefore that then means, so these are the BB acids, that then turns them into these soluble compounds which you can then use and put into fertilizers. So that brings us to the end. I know that's been a pretty sort of a whistle-stop tour, really, in 20 minutes, but that is all of the separates content on paper 2. My predictions in terms of paper 2 separates, I reckon that they could potentially ask a question on magnesium and acid as the rates practical. Could throw a bit of chromatography on there, and they could ask something around the ions required practical. So they'd be my 3 bets. I wouldn't bother with your sodium thiosulfate.